This is P. Mabu Hussain, Assistant Professor of EEE in Institute of Aeronautical Engineering, Hyderabad. So today in this video, we are going to discuss about the inductance of three-phase symmetrical line as well as inductance of three-phase asymmetrical line without transposition. So what is the symmetrical line and what is asymmetrical line? So let us see first. Right. So if you observe the first figure here, so the first figure represents the symmetrical line. So in this symmetrical line, you will be having three conductors which are equidistant from each other. Right. If you observe a three-phase transmission line in which you are having the three conductors A, B and C. Now if you observe the distance between any two conductors, so the distance will be the same. So in such a case, such type of transmission line is called a symmetrical transmission line, symmetrical three-phase transmission line, you can say. Right. Suppose in contrast to that, so if you observe the second figure, the distance between any two conductors is not same in this second figure. So that means if you observe a three-phase transmission line in which A, B, C are the conductors, so then the distance between A and B is D12. It is not equal to the distance between B and C, which is D23, and is also not equal to the distance between A and C, D31. Okay, so even though if the two distances here are the same and it is not equal to the third one, so then also in such a type of transmission line you can call it as a asymmetrical or unsymmetrical transmission line. Suppose D12 may be equal to D23. So but if it is not equal to D31, in such a case also you can say that this type of transmission line is a asymmetrical or unsymmetrical transmission line. Right? If all the distances, so if you observe, so the distance between any two transmission lines, two transmission line conductors, so then in such a case, if the distance is same, right? All the distances are same. In such a case, such type of transmission line is called a symmetrical transmission line. Now we are going to derive the inductance equation for this symmetrical line as well as this asymmetrical line. So first see the inductance of three-phase symmetrical line. Right, we are going to calculate the inductance for a three-phase symmetrical line. Here, let us assume that a three-phase transmission line is having three conductors represented by A, B, and C, and the distance between the any two conductors is capital D. Okay, as it is a symmetrical transmission line, all the distances, if you observe, those are same. So that distance we are assuming to be equal to capital D, and also assume that the current flowing through conductor A is IA, and conductor B is IB, and conductor C is IC. Okay, and these all three conductor currents will be such that sum of all currents IA plus IB plus IC. So this will be equal to 0. Okay, so now whenever conductor A carries the current, it produces some amount of flux. In similar way, conductor B and conductor C also produce some amount of flux. Now, let us see the flux linkages of conductor A. So, due to the current flowing in all the three conductors, right? So, if you write the flux linkages of conductor A due to current flowing through its own, so that means which is IA. So, then in such a case, you can write it as the flux linkages will be 2 into 10 power minus 7 ln. So 1 by DAA into IA. So this is the flux linkage of conductor A due to its own current. Okay. So in similar way, if you observe the flux linkage of conductor A due to current flowing in the conductor B, so then that value is 2 into 10 power minus 7 IB into ln 1 by distance between conductors A and B, which is capital D, or you call it as DAB. So then if you observe the current IC and if you find the flux linkage of conductor A due to current flowing in the conductor C, so that value will be 2 into 10 power minus 7 IC into ln 1 by the distance between A and C, so which is DAC. Okay. So now the total flux linkage of conductor A will be equal to, so flux linkage of conductor A due to its own current plus flux linkage of conductor A due to current flowing in the conductor B, so this value plus the flux linkage of conductor A due to current flowing in the conductor C also. So this value. So in all the terms you are having 2 into 10 power minus 7, it is common. So if you take that 2 into 10 power minus 7 as common, so then the remaining terms will be IA into ln 1 by DAA plus IB into ln 1 by DAB plus IC into ln 1 by DAC. Okay. So this is the flux linkage of conductor A. So due to current flowing in the all three conductors. Okay. So but here if you observe, this is a symmetrical transmission line in which all the distances DAB, DBC and DCA, all the distance will be the same, which will be equal to capital D here. And the self distance DAA or DBB or DCC. So this value will generally take it to be equal to R dash. Okay. So R dash is the geometric mean radius and this value is 0.7788 times the radius of each conductor. Okay. So now if you substitute these values here in this equation, okay. So DAA is R dash and DAB and DAC. So these two are capital D. So here if you substitute, then the flux linkage of conductor A due to current flowing in all the three conductors will be lambda A is equal to T into 10 to the power of minus 7 into IA ln 1 by R dash plus IB ln 1 by D plus IC ln, so here ln, so IC ln 1 by D you will get. So in all the terms, if you observe these two terms, so here ln 1 by D is there, here also ln 1 by D is there. So if you can take it common, right? So then what you will get, lambda A is equal to 2 into 10 power minus 7 IA ln 1 by R dash. So if you take ln 1 by D as common, so then IB plus IC you will get from this equation. Okay. So here if you take ln 1 by D is common, then you will get IB plus IC, right? So this term we are going to write here. Okay. So and as already I told, so in a three-phase transmission line system, the algebraic sum of all the currents flowing in all the three conductors will be equal to 0, which is IA plus IB plus IC is equal to 0. So from this equation, IA will be equal to minus IB minus IC. So then this can be written as IA is equal to minus IB plus IC, or you can even write it as IB plus IC will be equal to minus IA. So here in place of IB plus IC, you can write the minus IA. So then this equation can be written as lambda A is equal to 2 into 10 power minus 7 IA ln 1 by R dash minus IA ln 1 by D you will get. Okay, in place of IB plus IC, you are going to write minus IA. Okay, so now here in these two terms, here you are having the IA and here you are having the IA. You take it common. So then this lambda A you can write it as 2 into 10 power minus 7 IA ln 1 by R dash minus ln 1 by D you will get. Okay. So now from this equation, you can write it as 2 into 10 power minus 7 into IA ln, so log A minus log B, if you use that formula, log A by B you will get. So 1 by R dash by 1 by D you will get, right? So this can be written as ln D by R dash. So the flux linkage equation for conductor A due to current flowing in all the three conductors will be equal to lambda A, so which is the value is 2 into 10 power minus 7 into IA ln D by R dash. Okay. So as I said, D is the spacing between any two conductors and R is the geometric mean radius. So this value will be equal to 0.7788 times the radius of conductor. Okay. So this is the flux linkage of conductor A. So similarly, you can write the flux linkage of conductor B and conductor C also for current flowing in all the three conductors. Right? If you write the flux linkage of conductor B also, you will get this equation as 2 into 10 power minus 7 IB ln D by R dash. Okay. So if you write for C, lambda C will be equal to 2 into 10 power minus 7 IC ln D by R dash. Okay. So like that you will get. Now once you know the flux linkages, so then you can determine the inductance of the conductor, right? So the inductance of the conductor A now will be equal to LA. So this LA value is equal to lambda A by IA, right? So flux linkages, from the flux linkages you can determine the inductance. So by equation, LA is equal to lambda A by current flowing through that conductor IA. Okay, so now, so from this equation, so lambda A by IA will be 2 into 10 power minus 1 this ln d by r dash. So LA will be equal to lambda A by IA, the value will be 2 into 10 power minus 7 ln d by r dash, and the units are here henries per meter. So the value of inductance here will be for 1 meter only. Okay, so if you want for 1 kilometer, you have to multiply this equation with 1000, so that you will get the inductance in henries per kilometer. Okay, so similarly you can find the inductance for conductor B and conductor C also. So those inductance will be the same as this value, 2 into 10 power minus 7 into ln d by r dash. So for a 3-phase symmetrical line, so the inductances for all the conductors will be the same. So which is lambda A is equal to lambda B is equal to lambda C. All the conductors will be having the same inductance in case of a symmetrical 3-phase transmission line. Okay, and the value of inductance will be 2 into 10 power minus 7 ln d by r dash. So units are henries per meter. Okay, if you want for kilometer, so this will be written as 2 into 10 power minus 4 ln d by r dash. Okay, henries per kilometer. Okay, to get the in kilo for per kilometer, so this equation should be multiplied with 1000, so that it will be converted into henries per kilometer. Okay, so this is the inductance of 3-phase line with a symmetrical spacing, right? And this inductance of 3-phase symmetrical line, it will be same as the inductance of a 2-wire line. Okay, if you observe the 2-wire line also, for each conductor, the value of inductance will be the same. Okay, so whether it is a single phase 2-wire line, or it is a 3-phase symmetrical line, in the both the cases, the inductance of each conductor will be the value will be the same. So that value is 2 into 10 power minus 7 ln d by r dash, henries per meter. Okay, right. So let us see the inductance of 3-phase line with asymmetrical spacing, so without transposition here. So how you can determine the inductance of 3-phase line? So for a asymmetrical spacing conductors, asymmetrical spacing conductors is nothing but, so the distance between any two conductors you observe, so then that will not be the same here, right? Suppose if you take a 3-phase transmission line in which you are having the conductors A, B and C. Now if you observe the distance between DAB or DBC or DCA, distance between any two conductors, so this DAB may not be equal to DBC and may not be equal to DCA, or even suppose if two are equal and it is not equal to the third one also, then in such a case also you can call that the 3-phase transmission line system is a asymmetrical transmission line system. You can call either it is asymmetrical or even you can call it as unsymmetrical line. Okay, so unsymmetrical line is a line in which you are having unequal distances between any two conductors. Okay, so they will be having different spacing between their conductors, and the radius of each conductor here we are assuming to be equal to r, right? All the conductors radius will be, we are assuming it to be equal to r. And now we also assume that current flowing in each conductor will be IA, IB, IC, and these values of currents will be such that sum of all currents is equal to 0. IA plus IB plus IC will be equal to 0. Okay, in a 3-phase transmission line system, the sum of all the currents will be equal to 0. Right? So now let us derive the inductance for this unsymmetrical transmission line. So for determining the inductance, first you need to develop the flux linkages of each conductor. Okay, first consider the conductor A here, right? So now for conductor A, what are the flux linkages? You have to right? So the flux linkage of conductor A. So due to current flowing in the own conductor, which is IA, and due to the current flowing in conductor B, which is IB, and due to the current flowing in conductor C, which is IC. Okay, so that value will be equal to 2 into 10 power minus 7 into current flowing in the conductor A, IA into ln 1 by DAA. So DAA you can write, so the DAA will be same as R dash. So directly I am writing here. Okay, IA into ln 1 by R dash plus IB into ln the distance from A to B, so which is DAB. So IB into ln 1 by DAB plus, so when you take the current IC, so that IC into ln distance from A to C is DCA or DAC. Okay, so IC ln 1 by DCA here. Okay, so this is the flux linkage equation for conductor A. Similarly, you can write the flux linkage equations for other two conductors also. So if you take the conductor B now, okay, so now what are the flux linkages of conductor B when due to the current flowing in all the three conductors? Okay, so all the currents you have to take IA, IB, IC. Okay, now if you take the first its own current, so then that value flux linkages will be lambda A is equal to 2 into 10 power minus 7 into, so if you take the flux same current, that means IB, so that the flux linkages will be IB into ln 1 by R dash. If you take the current IA here, so then that value will be equal to IA ln 1 by distance between B and A you have to consider, which is DAB. Okay, so plus due to current IC, the value of flux linkage will be IC into ln 1 by distance between B and C, which is DBC. Okay, so this is the flux linkage of conductor B. So similarly, you can express the flux linkage of conductor C also. Okay, if you write the flux linkage equation for conductor C here, so then that value will be equal to 2 into 10 power minus 7. And now if we consider the current IC first, so then IC into ln 1 by R dash you will get, plus then you consider the current flowing in conductor A, which is IA, so then IA into ln 1 by distance between C and A you have to consider, which is 1 by DCA. Okay, so plus if you consider the current flowing in conductor B, which is IB, so then due to this current, the flux linkage of conductor C will be IB into ln 1 by distance between B and C, so which is DBC. Okay, so these are the flux linkages equation for each conductor. Okay, right, here we are going to define a operator A here. Okay, operator A, so the value will be equal to e power j 120 degrees. Okay, so the value of A is equal to e power j 120 degrees, or you can even write it as 1 at an angle 120 degrees. Okay, so we are going to define operator A here. So the value of this A will be equal to 1 at an angle 120 degrees or e power j 120 degrees. Now this e power j 120 degrees you can write it as cos 120 degrees plus j sin 120 degrees. Okay, so this value will be equal to minus 1 by 2 plus j root 3 by 2. Okay, the value of A is this value. Okay, so we are defining an operator A. So here, so the value of operator is 1 at an angle 120 degrees, which will be equal to e power j 120 degrees. Now this e power j 120 degrees you can write it as cos 120 degrees plus j sin 120 degrees. Then cos 120 degrees value is minus 1 by 2 and plus j into sin 120 degrees value is root 3 by 2. So the value of A is minus 1 by 2 plus j root 3 by 2. Okay, so then what is the value of A square? So A square will be equal to e power j 120 whole square. Okay, this value will be equal to e power j 240 degrees. Okay, or you can even write it as 1 at an angle of 240 degrees. Okay, right. So now if you expand this e power j 240 degrees, then this value is equal to cos 240 degrees plus j sin 240 degrees. Now if you calculate these values, cos 240 degrees and sin 240 degrees, so then the value of A square will be equal to minus 1 by 2 plus j root 3 by 2 you are getting. I think it is minus. So once you calculate the sin 120 degrees or sin 240 degrees, so any one of these two you are getting it to be minus j root 3 by 2 here. So we will see, we will calculate the value with calculator. Let us see, sin 120. So sin 120, so this sin 120 is, so plus j root 3 by 2, and if you take sin 240 degrees, so then the value will be equal to minus root 3 by 2. Okay, so the value of A square will be minus 1 by 2 minus j root 3 by 2 you will get. Okay, so now if you calculate the value of this 1 plus A square, right? So now 1 plus A square, so this value will be equal to, so 1 plus A is minus 1 by 2 plus j root 3 by 2 plus A square value is minus 1 by 2 minus root 3 by 2, j root 3 by 2 you will get. Okay, so here minus 1 by 2 minus 1 by 2 will be equal to minus 1, and this j root 3 by 2 minus j root 3 by 2 will get cancelled, so that the value will be 0. So 1 plus A square value will be equal to 0 here. Okay, right. So remember that the value of A here is 1 at an angle 120 degrees. So I am writing here. So A value, if you take this value, 1 at an angle 120 degrees, and A square value is 1 at an angle 240 degrees. A square is 1 at an angle 240 degrees. Okay, so 1 at an angle 120 degrees. So this value will be same as 1 at an angle minus 240 degrees. Both are the same. Similarly, 1 at an angle 240 degrees is same as 1 at an angle minus 120 degrees. Okay, right? If you take any reference, right? So reference 0 degrees. Now if you measure from this side, so if you get this is to be a 240 degrees, so 180 plus remaining. Okay, so then if you measure from this side, this value will be minus 120 degrees. So 1 at an angle 240 degrees, you can write it as 1 at an angle minus 120 degrees. In similar way, so if you take a reference 0 and if your angle is 120 degrees, if you measure from this side, so then if you measure from this side, you will get minus 240 degrees. Okay, so you can write A will be equal to 1 at an angle minus 240 degrees, A square will be equal to 1 at an angle minus 120 degrees. Okay, so you remember these 2 points which are helpful while calculating the flux linkages. Okay, so I will erase this again. Okay, so in a 3-phase transmission line system, you know that the values of currents will be same for a balanced 3-phase transmission line system. If you observe the magnitudes of IA, IB and IC, so magnitudes of currents IA, IB, IC, so this magnitude will be the same. Okay, so if IA is having a magnitude IA, so then IB also, it will be having the same magnitude, IB also the same for a 3-phase balanced system. Okay, for a 3-phase balanced system, the magnitude of all the currents will be the same. So we are considering the value will be equal to IA for all. Now if you take the angle, so IA will be, if it is at 0 degrees, then IB will be at a minus 120 degrees, IC will be at a minus 240 degrees. Okay, this is the representation of 3-phase balanced systems. Okay, right? Now, so this IA at an angle 0 degrees, simply you can write it as IA. Okay, so now IA into 1 at an angle 120 degrees here. So 1 at an angle 120 degrees, this you can write it as this is 1 at an angle minus 120 degrees. So 1 at an angle minus 120 degrees, you can write it as A square. So the value of IB is equal to A square into IA. Okay, and IC value is IA into 1 at an angle minus 240 degrees. Right. So now 1 at an angle minus 240 degrees, the value is A here. So in place of 1 at an angle minus 120 degrees, you can write A. So the value of IC will be A into IA you will get. Okay. So from this, the phase current IA will be same as IA, and phase current IB will be equal to A square into IA, and phase current IC is equal to A into IA. Okay, so that you are going to write here. IA is same as IA, and IB is equal to A square into IA, and IC is equal to A into IA. Okay, so now these equations we are going to substitute in flux linkages equations. Okay, here we are going to substitute the value of IA, IB and IC. Okay, so first you take the first expression. Okay, so if you take the first expression, so the flux linkage of conductor A is lambda A is equal to 2 into 10 power minus 7 IA into ln 1 by R dash plus IB into ln 1 by DAB plus IC into ln 1 by DCA. Okay, so now here in place of IB you can write A square into IA. In place of IC you can write IA into A. Okay, so now here in after writing the values of IB, IC in terms of operator A here, so then in all the three terms you are having IA as common, so you can take IA as common. Then this equation can be written as 2 into 10 power minus 7 into IA into ln 1 by R dash plus 1 by A square into 1 by, so ln value ln 1 by DAB plus A into ln 1 by DCA you will get. Okay, so that value we are writing here. So after substituting the values of IB and IC in terms of operator A, so the value of flux linkages will be lambda A is equal to 2 into 10 power minus 7 IA into ln 1 by R dash plus A square into ln 1 by DAB plus A into ln 1 by DCA. Right. Similarly, you have to write the flux linkage of conductor B, which is lambda B, in terms of IB here. In terms of IB, you have to represent. Okay. Right. So here lambda B is equal to 2 into 10 power minus 7 IB into ln 1 by R dash plus IA ln 1 by DAB plus IC ln 1 by DBC. Now here the value of IA and IC, so these two you have to express them in terms of IB. Okay, so how from these equations only, right, in terms of operator A, how you can express them? So from this equation, if you see, so from this equation the value of IA will be equal to 1 by A square into IB. Okay, so which is nothing but the A square value is 1 at an angle 240 degrees. Okay, you can take 1 at an angle 240 degrees into IB. Okay, this can be written as IB into at an angle minus 240 degrees. Okay, so now 1 at an angle minus 240 degrees, it will become A here. So this value will be equal to A into IB. So the value of IA is equal to A into IB. Okay, so similarly if you write for this equation, okay, so IC is equal to A into IA. So now IA in terms of IB is A into IB. You substitute here A into, in place of IA, A into IB you can write. So this value is equal to A square into IB. So the value of IC in terms of IB is A square into IB, and the value of IA in terms of IB is A into IB. So those two you are going to substitute here, right? The value of IA here is A into IB, and the value of IC is A square into IB here. So now in all the terms you have the term IB as common. Okay, so when you take it IB as common here. So the lambda B you can write it as 2 into 10 power minus 7 into IB into ln 1 by R dash plus A into ln 1 by DAB plus A square into ln 1 by DBC you will get. Okay, so this equation you will get after substituting the equation, these two equations. IC is equal to A square into IB and IA is equal to A into IB in the lambda B equation, right? So that you will get this equation. Okay, I am repeating here. Okay, so lambda B is equal to 2 into 10 power minus IB into ln 1 by R dash plus A into ln 1 by DAB plus A square into ln 1 by DBC. So this is the flux linkage of conductor B in terms of operator A here. Okay, so first equation is flux linkage of conductor A in terms of operator A. Okay, similarly you write for flux linkage of conductor C also. Okay, so this value in terms of IC and operators A you have to write. So for this you have to use the final equation. Okay, erase this. So here this from this equation and here from these terms. Okay, so IA is equal to IA initially, IB is equal to A square into IA, IC is equal to A into IA, right? So from these equation you have to write the IA and IB in terms of IC. Okay, so here IC you have to fix it as it is. Now IA and IB in terms of IC you have to write. Okay, so now how you can write this? From this equation the value of IA in terms of IC will be equal to 1 by A into IC. Okay, so now what is the value of A here? A is equal to 1 at an angle 120 degrees. So which will be same as 1 at an angle minus 240 degrees. Okay, and A square will be equal to 1 at an angle 240 degrees, which will be same as 1 at an angle minus 120 degrees. Right? So now IA is equal to 1 by A into IC you got. So this will be same as 1 by, in place of here you can write 1 at an angle 120 degrees into IC. So this can be written as 1 at an angle minus 240 degrees into IC. So 1 at an angle minus 120 degrees will be equal to, so minus what? Minus 240 degrees. Sorry, minus 120 this one. Okay, this is minus 120. 1 at angle minus 120 degrees is A square value. So A square into IC. So the value of IA is, in terms of IC is A square into IC. Right. Similarly, the value of IB here from this equation, so it will be equal to A square into IA here. Okay, so A square into IA. So now the value of IA is A square into IC. So total you will get A power 4 into IC here. Right, A power 4 is in the sense 1 at an angle 120 degrees whole power 4 into IC. Okay, so this you can even write it as e power 240, 120 into 4. So 120 into 4 you can write it as 480 into IC. Okay, so or from this equation if you write A square whole square you will get A power 4, right? So that A power 4 is equal to 1 at an angle minus 120 whole square you can write. Okay, so which is nothing but E power minus J 120 whole square. So which will be equal to E power minus J 240 degrees. Okay, so which is nothing but 1 at an angle minus 240 degrees. Okay, so A power 4, so you can write it as 1 at an angle minus 240 degrees into IC. So 1 at an angle 240 degrees. So from this equation this value is equal to A. So A into IC. So the value of IB is equal to A into IC and the value of IA is A square into IC. So those two terms you have to substitute here. The value of IA is A square into IC. So this is A square into IC and the value of IB is A into IC. So now if you observe in all the three terms you have IC as common. So if you take it outside, so then this equation can be written as 2 into 10 power minus 7 IC into ln 1 by r dash plus a square into ln 1 by dca plus a into ln 1 by dbc you will get. Okay, so this is about the flux linkage of conductor C, which is lambda c, right? So the same equation we are represented here in this slide, right? Again we repeat it. So lambda c is equal to 2 into 10 power minus 7 ic ln 1 by r dash plus a square into ln 1 by dca plus a into ln 1 by dbc. Okay, now these are the flux linkages of conductor A, conductor B and conductor C. So once you know the flux linkages, you can determine the inductance. So by using the expression L is equal to flux linkages by current flowing through that conductor. Okay, so if you want the inductance of conductor A here, so then the value will be flux linkage of conductor A by current flowing in the conductor A. So LB will be equal to, so flux linkage of conductor B by current flowing in the conductor B, and LC will be equal to flux linkage of conductor C by current flowing in the conductor C. So from these equations, so you can simply write. So here we are having the lambda A, and this side we are having IA, sorry, right? Lambda by IA will be equal to 2 into 10 power minus 7 ln 1 by r dash plus a square into ln 1 by dab plus a into ln 1 by dca. Okay, like that you can derive the inductance of conductor B and conductor C also. So then the final values of inductances for all the three phases will be, so LA is equal to 2 into 10 power minus 7 ln 1 by r dash plus a square into ln 1 by dab plus a into ln 1 by dca. So this is the inductance of phase A. So inductance of phase B is LB. So this value is equal to 2 into 10 power minus 7 into ln 1 by r dash plus a into ln 1 by dab plus a square into ln 1 by dbc. So this is the inductance of phase B. And finally inductance of phase C. So that value will be equal to 2 into 10 power minus 7 ln 1 by r dash plus a square into ln 1 by dca plus a into ln 1 by dbc. Okay, so these are the inductance equations for each phase in a three-phase asymmetrical transmission line. Okay, as you know, asymmetrical transmission line in the sense the spacing between the two conductors, if you observe, so those are not the same. Okay, so now for a asymmetrical three-phase transmission line, if you observe the inductance equations, so which are all these three equations, right? So the value of inductance is not same. Okay, the value of LA, LB and LC. So the value of inductances are not same. So which means that the reactance also not same. Okay, when the inductances are not same for each phase, then reactance, so reactance X will be equal to omega into L. So right, so that depends upon the length of the inductance of the that particular line, right? So for if you calculate the inductance of phase A, so which is XA, so that value will not be equal to inductance of phase B, and that value not equal to inductance of phase C. Okay, so the inductances are not same in all the three phases for a three-phase asymmetric line. So the reactances also will be the not same. Okay, so when the reactances are not same, what about the impedances? Z is equal to R plus JX. So this impedance is also not same. ZA, ZB and ZC. Okay, inductance of all the three phases will be different. Okay, so when the values of inductances are different, what is the disadvantage? So we will see here. Okay, so if you take a three-phase transmission line, okay, right, so you take a three-phase transmission line in which you are having three-phase conductors. Okay, so you consider that these three-phase transmission line system is a unsymmetrical transmission line. That means if you observe the distance between any two conductors, so that particular distance will not be the same. Okay, in such a case, that type of transmission line is a asymmetrical transmission line. Now, if you supply the three-phase from the sending end, so three-phase balanced supply, So if you give here at the sending end, and if you observe the receiving end, okay. So now at the receiving end, you will not get a balanced three-phase voltages or balanced three-phase currents. So why? Because for a unsymmetrical transmission line, so the inductances for each phase will be different. So when the inductance is different, then reactance also will be different. Then the impedance also will be different. Inductance of line A will be so ZA, so which will be not same as ZB and is also not same as ZC. So ZA, ZB, ZC all are different. In such a case, the drop across the impedances, voltage drops will be the different. So at the receiving end, you will not get the balanced voltages. So which is undesirable. Okay. So in a three-phase transmission line system, if the conductors are not spaced symmetrically, which means that if they are placed asymmetrically, so in such a case, the value of impedances are not same because the inductances are not same. So because of that reason, even if you supply a balanced three-phase supply at the receiving end, at the sending end, you will not get the balanced voltages. You will get the unbalanced voltages, right? So the unbalanced voltages will affect the equipment connected at the receiving end. So unbalanced voltages are not desirable. So because of that reason, this asymmetrical transmission line are not preferred for transferring the power from one end to the other end, right? So but here you can make these unsymmetrical transmission line inductances will be the same. So by taking the transposition, so you have to transpose the transmission lines at regular intervals, so that the inductance of all the phases you will get same, so that balanced voltages you will get at the receiving end. So what is this transposition? How you can achieve the inductance of this transposed transmission line? We will discuss in the next video. So, so as I said, as the inductances are inductances given here, so with these equations are not same, so these are undesirable. So because they result in unbalanced circuit configuration. Okay. So this is how you can determine the inductance of a three-phase symmetrical line as well as inductance of a three-phase unsymmetrical transmission line. So for unsymmetrical transmission line, without transposition we discussed today. Okay. So with the transposition, you will get the balanced inductances, so that means balanced voltages at the receiving end. So because the average inductance in a transposed transmission line will be the same in each phase. So that we will discuss in the next lesson. Okay, thank you very much.
Like, share and subscribe. Hit the bell icon for more updates.